Okay, it's being recorded. Let's see. I may just jump directly to the sharing the screen here.
Hey, do you know when our test redos are going to be returned?
This week. You mean your test ones?
Yeah.
Yeah, yep, I was starting on those last night. And actually, this is not an efficient process. I had to make an Excel spreadsheet that has each of the problems and problem parts listed and how many points they were, and then the individual scores by person. And then when I'm doing the retakes, I have another row where I put the new individual scores per person. And I've got to come up with a more efficient method of doing this in the future because this was just kind of crazy. But anyway, we'll see. It might almost have been easier just to have you redo the test and then grade it that way and just calculate the averages. That might have been quicker, but too late now. Already set that up. Yeah, but it should be. I'm working on it this week. Although, let's see. I think I can do it while I'm giving astronomy tests today too. So I can sort of double up on my responsibilities for a while. Okay, yesterday we started looking at something called spring potential energy, and it shows up in a lot of applications. So we'll be able to use those things. And I wanted to look at a couple problems with that here today. And then we can actually start power today or tomorrow as well. So I don't remember what I put for the due date on those homeworks, but I might have to bump them by a day or so. Anyway, instrument known as an atomic force microscope. So it can be used to measure forces between atoms or molecules at the nanometer scale. And here they've got an indentation measured in nanometers. So maybe that wouldn't hurt so much as I think, because that's not a whole lot, but it might be enough to stimulate a nerve ending. Who knows? Suppose you find the elasticity of biological membranes by using or measuring the indentation of the force probe into the membrane as a function of the applied force. So you could then use an AFM, atomic force microscope, to study the elastic properties of the capsid, the outer shell of a virus. Okay, as long as they're picking on viruses, that doesn't bother me. All right, the graph shows you data of the force applied to the capsid by the AFM in nanonewtons, nanonewtons and nanometers, versus the indentation of the capsid. What is the effective spring constant of the capsid for indentations of 0 to 14? Okay, that's this little stretch here, where it's actually pretty linear as far as its motion, and we could extend that line out if we wanted to and have a bigger batch to mess with. But it looks like, let's see, actually, if we extend the line, our slope would be 1.4 nanonewtons divided by 50 nanometers. So now the reason I want to get that slope is because the force, the applied force here, is going to equal the effective spring constant times the indentation amount, if we think of this as the x direction here. So K is going to be the slope of that line. And because I extended it out, I'll make a smaller error in guessing what these things are than if I had not done that. So the slope of this thing will equal 1.4 nanonewtons divided by 50 nanometers and I can just divide out the nano part, because in both cases it means times 10 to the minus ninth as a multiplier, and common multipliers you can divide out. So the slope of that thing will be 1.4 divided by 50, which is about 2.8 times 10 to the minus 2 newtons per meter. Or you could call it nanonewtons per nanometer too if you wanted to, but that's what you would get. How much elastic potential energy is stored in the membrane when it is indented 14 nanometers? Holy smoke. Okay, well, that's the old, the energy stored in there. And a lot of times we'll put U sub EL or something to that effect to show that it's elastic potential energy, but it's going to be 1/2 kx squared. And this will work. My k is in that. And if I write it as 1/2 times 2.8 times 10 to the minus 2 newtons per meter times, I'm compressing it by 14 nanometers, that's the x, so 14 times 10 to the minus ninth meters, and that has to get squared. And so by converting this thing into meters, or by replacing the nano with times 10 to the minus ninth, I'll be squaring that times 10 to the minus ninth, and I'll end up with Newton meters for units when I'm done, because meters squared times newtons over meters is a Newton meter, and those are joules. So I'll probably be able to write it as some tiny multiple of a joule. Here's a nice example of using scientific notation on a calculator. I'll have 0.5, which is 1/2, times 2.8, which was stored anyway. I could have just recalled it. EE minus 2 times, now I'm going to put that number in here, the 14 EE minus 9, and I want to square it. And if I hit the x squared button, it only squares the last number that I put in there. But because I'm using scientific notation, the 14E minus 9 is treated as a single number in computer memory. So if I just hit squared, that's the only thing that's going to get squared, is the 14E minus 9. Oh, and it will square the 14 and the minus 9. So it'll do the calculation correctly. Whereas if you put scientific notation in by going 14 times 10 to the minus ninth and then hit the squared key, it would only square the times 10 to the minus ninth. So using the scientific notation function saves you steps in your calculation. And I get 2.74. I can only keep 2 sig figs. So 2.7 times 10 to the minus 18th joules, which is not much. This is actually something that would be better measured in a little unit called an electron volt. And it would be a few of those. In fact, yeah, it would be 17 electron volts if you were using those units of energy, but we're not going to be learning about them. If you've taken chemistry, you might have heard of the unit of an electron volt, but we'll pass on that for now. So anyway, that's applying the ideas of this elastic potential energy. One, that the force is equal to the effective spring constant times the compression, in this case, the indentation. And then the other is that elastic potential energy is 1/2 kx squared. So that's worthwhile. Okay, here's one that could save your life. Who knows? Jorge is going to bungee jump from a bridge that is 55.0 meters over the river below. The bungee cord has an unstretched length of 27.0 meters. To be safe, the bungee cord should stop Jorge's fall when he is at least 2.00 meters above the river. And if he has a mass of 75.0 kilograms, what is the minimum spring constant of the bungee cord? I'm not sure I would trust this calculation to somebody at a bungee jumping cord site or a bungee jumping site, but they probably have somebody who studied some physics and knows about the spring constants of their cord would write up some sort of a table so Jorge doesn't have to know his physics all that well. Or no, not Jorge, but the guy running the thing. So at any rate, let's see what happens in this case. And I'll draw a picture to illustrate what's going to be happening here. So here's Jorge standing above the river with this thing tied around his ankle. And then it's probably coiled up there on the top of the thing and tied on. And the river is down here, 55.0 meters from where Jorge is to where the river is. However, we want to stop him 53 meters down because we want him to stop 2.0 meters above the river. 2.00 meters above the river. Not that we need that much precision because we don't have anything else to that precision. And the bungee cord has an unstretched length of 27 meters. That means Jorge is going to fall for 27 meters before he even starts to slow down. So that would be kind of thrilling to fall that far. Yeah, that's 90 some feet. Oh, great. Anyway, that's kind of the situation that we have here. And I'm going to choose this point 2 meters above the river to be where my gravitational potential energy is equal to 0. So it's 53.0 meters that I'm going to care about here. Okay, so here's where U elastic, or no, U grav is equal to 0, is right at that level. I could set it equal to that at the river level, and then at this point, when he's down that far, he'll be stopped and he'll still have some gravitational potential energy, but it turns out it doesn't matter where I set the 0 level for. So this is going to be a conservation of energy thing, and we're going to bypass completely the intermediate stages where Jorge has kinetic energy. He has none at the top. We want him to have none at this point as well, because we want him to be stopped 2 meters above the river. And so we'll see what happens with that. So initial, final, and I'm going to make 3 columns, although one of them is going to be 0. I'll have kinetic energy that we could consider, but we're not going to here. I'll have gravitational potential energy, and I'll have spring potential energy. And those will be the same 3 things that I consider over here. Ke, U grav, U elastic. And I guess I could call these GPE, gravitational potential energy, and SPE, spring potential energy, but these work okay. All right, well, there's no kinetic energy at the start. There's none at the end. He's going to be stopped. So this is kind of neat that you can do with energy considerations. You can skip over all the intervening stuff. I'm going to define 53.0 meters to be H, okay? And initially, there will be gravitational potential energy. MGH is what I'm going to have. There's going to be no elastic potential energy because the cord doesn't start to stretch until he reaches this point. And that's where all the energy is going to go in stopping him when he gets down here. So that's our initial energy. In the final case, there's no kinetic energy. There's no gravitational potential energy. I can put plus signs between these. And all we're going to have is 1/2 kx squared, where x is going to equal 53 meters minus 27 meters. So 53.0 meters minus 27.0 meters, and I think that's 26.0 meters. And that's x, the x that I've got here. So mgh is going to equal 1/2 kx squared. We know the mass of Jorge, we know g, we know h. We know how much the bungee cord will be stretched by. The only thing we don't know is k. And so we can solve for that. This time I don't have stuff canceling out on either side or dividing out. I don't have a common, in the ones we've done up until this time, everything depended on the mass, the kinetic energy and stuff like that. But now we've got something that does not depend on the mass, so I can't divide the mass out. But anyway, I can divide both sides by 2 and divide by k, and I will get 2, or no, divide by x squared. I'll do it in 2 steps. 2 mgh is equal to kx squared. K is the thing I want, so I'll divide out by x squared. That will equal k, but I'm going to put the equal k on this side and then plug in the numbers. 2 times Jorge's mass, 75.0 kilograms, times 9.81 meters per second squared, 0.81, times h, which is 53.0 meters. And I divide by x squared, which is 26.0 meters squared. Okay, let's look at the units. Here we've got kilogram meter per second squared times meters. And that's on top. And on the bottom, I've got meters squared. Well, let's see. What am I going to get out of that? If I think of this as a Newton, and don't try to combine these two units, I'll have Newton meters on top and meters squared on the bottom. I'll end up with newtons per meter for my spring extension force. Otherwise, I would get, kilogram meters squared per second squared divided by meters squared. Those will divide out, and I would get kilograms per second squared. Turns out this is the same as a Newton per meter, because a Newton has a kilogram meter per second squared in there. But we understand a spring constant better if we think of it as newtons per meter instead of kilograms per second squared. So let's find out just how strong this bungee cord has to be. Let's see. 2 times 75 times 9.81 times 53 divided by 26 squared. And it's a little stronger than the springs I've got in the classroom. This ends up being, I think I've got 3 sig figs on everything. I do. 150 15 newtons per meter, which is, I think the ones I've got out in the classroom are maybe 10 newtons per meter or 9, something like that. So this is a lot stronger than those things. And that's good, because if it wasn't, Jorge's going to smack his face into the river, and that would hurt if you're still going at a good clip. So, okay, let me real quick show you on this problem how we could do it if we chose the bottom of the river, or the river level, to have be our zero of gravitational potential energy. And so in that case, we would have H equaling 55.0 meters. That would be H initial, and H final equaling 2.00 meters. Well, our initial energy would still be mgh initial. So I'd start off with mgh initial, that's my initial energy, is going to equal 0 plus, now our gravitational potential energy 2 meters above the river is going to be mgh final, and plus that 1/2 kx squared. Okay. Well, we're after the k still, and so I'd get the other stuff, this over on the other side, and I would have mgh initial minus mgh final, which is mg times h initial minus h final. But h initial is 55 meters, h final is 2 meters. That's going to be mg times 53.0 meters will equal the 1/2 kx squared. And this is exactly the equation that we ended up with here. We said that h was 53 meters. So you end up with the same equation no matter where you set the gravitational potential energy equal to 0. I could have set it equal to 0 up here and said that h final is negative 53.0 meters if I wanted to. But what matters is the difference in gravitational potential energy between initial and starting point. And that'll be the same no matter where you set the 0 at. So something to keep in mind for those things. Okay, here's a sort of odd little problem, I guess. A 2-kilogram block is released from rest and allowed to slide down a frictionless surface and into a spring. The far end of the spring is attached to a wall, as shown. Frictionless surface. Okay, that means no energy is going to be lost here. The initial weight or height of the block is 0.50 meters above the lowest part of the slide, and the spring constant is 450 newtons per meter. What is the block's speed when it is at a height of 0.25 meters above the base of the slide? So here we're going to say that it is 0.50 meters above the slide. And then we would want to know what is its speed when it's 0.50 or 25 meters, excuse me, above the slide. And then it asks how far is the spring compressed, and the spring sends the block back to the left. How high does the block rise? Well, I'm going to answer that last question first. If there is no friction, there's no energy lost in this system. What's going to happen is this mass slides down here, moves along this part at constant speed, runs into the spring and compresses it, and gets sprung back out with no loss in energy. It'll end up going just as high as it started from. And there's where it stops, and then it'll just come back down and repeat that motion. And with no friction, no way to lose energy, it just keeps doing that all day. So that would be the case. It's kind of an unreal situation, but it's easier to do the calculations that way. So for this part A, here's what we're going to have initially. We will have an initial energy of mg h initial, where h initial is 0.50 meters. And that initial energy will equal the energy that it has when it's here, which is going to be mg h final, where h final is 0.250 meters, half of what we had before, or not an extra zero on there, just 0.25 meters, although we do have a zero on that one. Okay, but there's going to be kinetic energy at this point, 1/2 mv squared. Now, we haven't entered into the part yet where it's in contact with the spring. And once it contacts the spring, then we'll have to take into account a 1/2 kx squared thing, but we don't have to worry about that just yet. And here we've got everything, every term we've got has an m in it. So that means that I can divide those out and say that gh sub I equals gh final plus 1/2 v squared. Whoops, this is supposed to be a plus sign. There we go. Now, if I subtract this away, I'll have g h initial minus g h final is going to be 1/2 v squared multiplied by 2. Well, h initial, this would equal g times h initial minus h final. And h initial minus h final is going to be 0.25 meters, 0.50 minus 0.25 meters. So I'll have 9.81 meters per second squared times 0.25 meters, just 0.25 meters. Oh, I'm going to multiply both sides by 2. So 2 times that, and that'll be v squared. So, which will equal, may as well calculate it while I'm at it here. And I get 4.9 meters squared per second squared. And then I just take the square root of both sides, and I get that when the block is 0.25 meters above the base level, it'll have a speed of square root of that, 2.2 meters per second. And when I multiply meters by meters squared per second squared, I got the meters squared per second squared. Keep track of your units at every step in a calculation. And also start off with variables or equations in variable form first. Don't just dump the numbers into them, because if you screw up that number dumping and get everything wrong from there on out, you don't get partial credit. Whereas at least if you have that in there, I know that you were on the right track from the start. Okay, so 2.2 meters per second for part A. Part B says, how far is the spring compressed? Well, I'm going to move over here to do that. And here's what's going to happen for part B. Instead of having an mgh final here and a 1/2 mv squared, I'm going to start with that thing being the block being at rest here and ending with the spring being fully compressed and the block being brought to rest there. So I will have mgh initial. At the end, all of the energy is going to go into a compressed spring, 1/2 kx squared, and it'll be compressed by a distance x. I'm given the spring constant. The only thing I don't know in this equation is x. So if I multiply both sides by 2 mg h sub I is equal to kx squared. By the way, getting that equation is the big conceptual hurdle on this question. So let's see, and then divide both sides by k, and I'll get x squared is equal to 2mg h sub I over k, which finally we can just say 2 times the mass, 2.0 kilograms. I may as well just write acceleration due to gravity as 9.8 meters per second squared. And h sub I was 0.50 meters. So that's the whole numerator. And then K is 450 newtons per meter, which is a pretty strong spring. That's 45 times as strong as the ones I have out at school that we do experiments with. So 2 times, guess I could have done some of that in my head, divided by 450. And I get x squared is equal to 4.4. Okay, unit-wise, what are we going to get? Remember, a Newton per meter was a kilogram meter per second squared is a Newton. So this Newton on top will divide with that Newton, and I'll have 1 over meters on the bottom, which will flip up top and give me meters squared. So, whoops, 4.4 times 10 to the minus 2 meters squared. So taking the square root of that, I get x is equal to 0.21 times 10 to the minus 1. Oh, nope, it's actually 0.21 meters, which could be written as 21 centimeters if you wanted to, but 21 hundredths of a meter, which is about that much, is how much it compresses by. So that works out. Okay, I do want to do this one. We'll just do this one example of, no, I want to start with power. And so we can get going a little ways on that here. And then I'll do this problem maybe tomorrow after we've done a few of the power problems. And we'll see how those things work. Power has a couple of meanings, but one of them is the rate at which work is done. And anytime you have a rate at which something is done, you're going to have a delta T in the denominator somehow. And so if you're the thing doing the work, you can think the power is going to be the work that you do divided by some delta T. And so it'll be like that. Another definition of power is it is the rate at which energy is transformed from one type to another. Okay, well, it's got another rate in there, so it's going to have a delta T on the bottom. And in the numerator, in that case, it might just be some amount of energy E that's going to be happening. Let's see. Those are pretty good definitions of power, both of them. They seem like they're different, but it's always work is measured in units of joules, which are our measurement of energy. It's going to be energy divided by time, no matter what we happen to be doing. And our unit of energy is a joule. Our unit of time is going to be a second, at least for this definition. Sometimes we may have to do some unit conversion. And a joule per second happens to be a watt. And it's named after a guy named Watt. So when you write out his name, you get a W-A-T-T with lowercase, but the abbreviation will be an uppercase W, which can be sometimes confusing if you use the uppercase W for work. So be a little bit cautious with that, although the units of work are joules. So you can sometimes get a little bit mixed up with that kind of stuff. This is a table out of your book that has some power example problems. Well, this is power output or consumption, and it goes from something very energetic to something not so energetic. Supernova at its peak, 5 times 10 to the 37th watts that it puts out. Now, a supernova is an explosion of a star at the end of its life, either a massive star supernova, or there's another type called a white dwarf supernova, but they're both about equally bright, and they put out more power during that brief flash of the explosion than the entire Milky Way galaxy with all of its stars puts out. The Milky Way galaxy is the galaxy that we happen to be in, and the solar system is, about 2/3 of the way out from the center in, no, just a little bit more than halfway out from the center in one direction from the center. And anyway, the Milky Way galaxy has a range estimate of stars in it between about 100 and 400 billion stars, and the sun is just one of those stars. So that's kind of interesting. Pulsar, that's another astronomical thing, puts out 10 to the 28th watts. The sun puts out 4 times 10 to the 26th watts in solar energy. It's radiating it in all direction. We only get to capture a tiny bit of that, but that's all right. Then you start dropping off a long ways. A maximum eruption of a volcano, 4 times 10 to the 15th. A lightning bolt, 2 times 10 to the 12th. So the volcanic eruption at maximum is about 2,000 times as energetic as a single lightning bolt. Nuclear power plant. This is the total electric and heat transfer. One of the things they do is produce a lot of heat, but they also produce electricity. That's 3 times 10 to the 9th. 10 to the 9th is a billion. So 3 billion watts is what a nuclear power plant can put out, which is 3,000 gigawatts. Sometimes you'll hear that term. An aircraft carrier, total useful and heat transfer, 10 to the 8th. That would be 100 million or 100 megawatts. Dragster, actually that's 2 million watts or 2 megawatts. Car is not so energetic. It's about 8 times 10 to the 4th. That would be 80,000 watts. A football player is about 5,000 watts. And you can see various things in here. A person at rest around 100 watts and blah, blah, blah. Well, that's all heat transfer. And then there's total useful. Oh, that's just the heart. Okay. The person at rest. And an electric clock, 3 watts, which isn't much. A pocket calculator, 10 to the minus third. I don't know what a cell phone uses. That might be interesting to track down sometime. But those are some various power things there. Let's see. Let's do an example. A person in good physical condition can put out 100 watts of useful power for several hours at a stretch, perhaps by pedaling a mechanism that drives an electric generator. Okay, 100 watts isn't an awful lot, but you can do it for quite a long time. And the reason you can put out that much for that long is because when you're pedaling something like a bicycle, you're actually using the largest muscle in your body, which is your quadricep muscles in your legs. And those can go for a long time. Whereas if you were having to do this with your arms, you'd not be able to do it for several hours, that's for sure. Anyway, but if we neglect any problems of generator efficiency and practical considerations such as resting time, how many people would it take to run a 4 kilowatt electric clothes dryer? Well, if we let P sub 1 equal our 100 watts here, which is going to be, that's the power output of one person. Okay, and we want to run a 4 kilowatt clothes dryer. Well, that kilo means times 10 to the third. So that's the total power we're going to want. If we let N equal the number of people we'll have that we're going to need, if I just take N times the power output per person, that is what I want to equal that 4.00 kilowatts. Okay, so N is going to equal that 4 kilowatts, except I'm going to replace kilo with times 10 to the third watts, and then divide by P1, but I'm going to change P1 back into 100 watts. And so I'll get 4,000 divided by 100, which I'm pretty sure is 40. But I checked to be sure. Yep, it's 40. So you'd have to have 40 people. Now, here's a way you could trick them. You could set up an exercise center that has 40 stationary bicycles in it, and you could trick people into running your clothes dryer for you, and then you could do it. Okay. Now, that's all well and good, but how many people would you need to replace a large electric power plant that generates 800 megawatts? Well, we'll do the same thing. We'll have NP1, but this time it's going to have to equal 800 megawatts. And mega means million or times 10 to the sixth. So our N is going to equal 800 times 10 to the sixth watts, because that's what the mega part is, divided by 100 watts down here. And we'll get a number that's purely just a number, because it's just the number of people you'd need. So anyway, oh, well, piece of cake. Oh, I could have done that in my head. 800 divided by 100 is 8. You'd get 8 times 10 to the sixth people. Okay, that's 8 million people to run your 800 megawatt power plant. So it'd be hard to trick that many people into riding stationary bicycles for you 24 hours a day. but maybe. Okay. There's a unit in this thing. It's what's the cost of operating a 3-watt electric clock for a year if the cost of electricity is, that ends up being 9 cents per kilowatt. kWh is a kilowatt hour. And I'll show you what that happens to be. kWh. The K means 1,000. And that's just 1,000 is all it is. And that's watts, which is joules per second. But that hour is a unit of time. And turns out there are 3,600 seconds in an hour. So I can replace the hour with 3,600 seconds. And the seconds will divide out. Turns out that a kilowatt hour is some number of joules. It's a unit of pure energy. But that's what you pay for on your electric energy bill, your electric bill. And this ends up being 3.6 times 10 to the 6th joules, or 3.6 megajoules. So 1 kilowatt hour is 3.6 megajoules. Okay, million joules. All right, not that that may help us a lot, but we should be able to figure this out. Anyway, we have our 3-watt electric clock. Well, 3 watts means 3.00 joules per second, and we want to run it for a year. Okay, this is the rate of energy use in that clock, how many joules per second it uses. If I multiply that by the number of seconds in a year, I'll get the total energy it uses per year. And then I can figure out the cost of it. Okay, but let's figure out the number of seconds in a year. 1 year times 365.25 about seconds per year times, nope, that's days per year. I don't know what I was thinking, but we'll have 24 hours per day, and that'll divide out. The years will divide out. Now I'm down to hours times, we've got 3,600 seconds per hour. And so I'll be down to seconds when I get done here. And it's going to be about, I remember this number, about pi times 10 to the 7th, but not exactly that. So, oops, clear. And I didn't really need to include that extra 0.25 days, but that's about what it is. Yeah, it's about 3.16 times 10 to the 7th seconds. Okay, pi is 3.14 to 23 sig figs. And so this is a little bit more than pi times 10 to the 7th seconds. So that's how many seconds I've got. So I'll take this and multiply this by 3.16 times 10 to the 7th seconds. And I'll get, oh, just multiply it by 3. And I'll get 9.5 times 10 to the 7th joules. Okay, well, 1 kilowatt hour is 3.6 times 10 to the 6th joules, but 1 kilowatt hour costs, actually I convert this into kilowatt hours, or can, so 1 kWh over 3.6 times 10 to the 6th joules. And then I just put in the cost per kilowatt hour, 0.09 per kWh, and everything will cancel out or divide out. Not supposed to use the word cancel because it's not a well-defined mathematical term, according to a guy who used to teach here. Anyway, I'll just multiply this whole string of things here, or this string of things. So 9.5 times 10 to the 7th times my $0.09, and I divide by 3.6 times 10 to the 6th. And I'll get a princely sum of $2.40 if I round it to the nearest, or to two significant figures. So $2.40, which isn't bad. So is it worth unplugging your clock to save energy? Probably not. So now it would be worth it to turn off a 100-watt electric light bulb, because that's going to cost you a bit more. Okay, we'll stop there. We've done a couple of power problems. We can do some more of those tomorrow, and then I'd also like to do this last problem tomorrow as well. And that will kind of conclude our energy chapter once we get done with those things. So we won't be in too bad a shape, but I'll bump the due date on that homework here. I think I'll do that right now before I forget, or at least right now as soon as I log off here. Okay, stop the share there. And looks like we lost our audience. Anyway, I'll go ahead and postpone the due date on that homework for you. And
Do you know when you're gonna upload? I think it was yesterday's lecture.
let's see. I can do that. I think I may have uploaded it already, but I'll bump that up to YouTube and then connect it to our class.
All right, thank you.
Mm-hmm.